Hello, in this video we're going to continue our discussion on inner products, and the first thing that we're going to prove is the Pythagorean theorem. So let V and W be vectors in Rn and they are orthogonal relative to an inner product, then length of V squared plus length of W squared is equal to length of V plus W squared. So how is that related to the Pythagorean theorem? If you look at the Pythagorean theorem tells you if you have two vectors, if you have a triangle with a right angle on one of the vertices, then the legs squared is equal to the square of the sum of the squares of legs is equal to the square of the hypotenuse. So here I have to first talk about the notion of orthogonality, and we know how to do that. We say the inner product is 0. Now we'll have to somehow come up with a relation between the sides and the hypotenuse. So if you call one of these sides V and the other side W, then the hypotenuse is going to be V plus W. So this would be V plus W, and which is why we get this condition. Okay, let's actually prove this one. The proof is pretty straightforward. So this is like, I guess, an alternate way of proving the Pythagorean theorem, and in fact it can be proved in general. So let's start from the right side. In other words, it can be proved in any inner product, using any inner product. So this is equal to, by definition, this is the inner product of V plus W and itself. We will go ahead and use linearity with respect to the first component. So that would be V inner product of V and W, V plus W, plus inner product of W with respect to comma V plus W. So this is linearity with respect to the first component. Now we'll use linearity with respect to the second vector. So this would be V comma V plus V comma W plus W comma V plus inner product of W and itself. Okay, now inner product of a vector with itself is that norm, the length squared, plus, since the vectors are orthogonal, the inner product is 0, and these two are the same because of symmetry, and that gives us exactly what we want. So we started from square of the hypotenuse, which was V plus W. So the hypotenuse was V plus W. So the square of the hypotenuse ends up being the sum of the squares of the two legs. So this proves the Pythagorean theorem. Now let's move on and prove something very important. Now let me give you a background before I get to the Cauchy-Schwarz inequality. If you recall, one of the things that we proved was that if we have two vectors V and W, dot product of these ones is going to be norm of V, or length of V, times length of W times cosine of theta. Now I would like to define the angle between two vectors. One of the purposes of doing these inner products is to define the angle between two vectors. So I can simply evaluate for theta from here. So that would be dot product of V and W divided by product of their magnitudes. So the angle would be just cosine inverse of this quantity. But in order to be able to take cosine inverse, I would need to make sure that this quantity that I have is in fact between -1 and 1. So this quantity would have to be between -1 and 1. So the question is it true that this quantity is always between -1 and 1? So let's see if that's something we can prove. So let's look at the vector V. So what is the quantity that we're trying to prove? What is the inequality that we're trying to prove? We are trying to prove in general, and this is just for the particular case of inner dot product, but in general what we're trying to do is to show that this is less than or equal to, in absolute value, less than or equal to the product of the length of V and W. So this is the inequality that we are trying to prove. If we can prove this inequality, it means the fraction that I have here boxed in green is between -1 and 1, which means we can take the cosine inverse, and therefore we can define the angle between two vectors. Okay, so the question is, how do we prove this inequality? If you divide both sides of this by V, and for that by length of V, for that I need V to be non-zero. I get this. Now, intuitively, based on what we had seen before, this is essentially just the norm of W cosine of theta. So in Euclidean geometry, what happens is this angle is theta, and let me change this one to W. This angle is theta. So this one is going to be length of W times cosine of theta, and this angle is a 90-degree angle. Now I would like to show one leg of a right triangle is less than the hypotenuse. How do we show in a right triangle leg is less than hypotenuse? Well, you would use the Pythagorean theorem. So in other words, I will have to show that this length is less than the hypotenuse. But in order to be able to do that, I will have to first show that I do have a triangle which is a right triangle. So let's actually find the projection here. Find this length, green length here. So what is this length? The length of that is exactly that quantity, V inner product with W divided by norm of V. This is the length, and its direction is going to be in the direction of V. What is the direction of V? It is the unit vector in that direction. So I'll take the vector V and divide by its length. So this becomes the inner product of V and W divided by, well, at the bottom I have length of V times length of V. That's just length of V squared, and then times V. So this is the projection. This is the green portion. That's one side of the right triangle. The other side is this vector, which is just W minus that quantity, minus the inner product of V and W divided by norm of V squared times V. So if I use the Pythagorean theorem for these three vectors, then I should be able to get the final answer. Okay, so let's turn that into a proof. So assume first that W isn't 0, and the case when W is 0 is in fact one of your exercises. So let's assume W is not 0. So what do we do if W, or I guess V, is not 0? In that case I chose V to not be 0. So assume V isn't 0. If V is not 0, consider these two vectors. Consider W equals, let's see what we had. We had inner product of V and W divided by norm of V squared times V plus, okay, so let's mention that inner product of V and V is not 0. This is positive, in fact, by positivity. So consider this plus W minus that quantity, inner product of V and W over norm of V squared times V. So this vector plus this vector. We will show that these two vectors are in fact orthogonal so that we can use the Pythagorean theorem. So let's take the inner product of these two. So inner product of this vector, which is a multiple of V, and the other vector, which is W minus okay, so we'll evaluate these. Hopefully this ends up being 0, and if we can show that this is 0, then we should be basically done. So this is equal to, we'll use linearity. We take out, so notice that there's actually some constants here. This is a scalar, well, not constant, scalar I mean. So this is a scalar, this is also a scalar. So those would come out. So if you take out those scalars, you'll be able to do linearity with respect to the first component and the second component. So this is VW over length of V squared times the inner product of V and W minus, and then those scalars come out, we get VW squared over length of V to the power of 4, because we have length of V squared times length of V squared times V inner product with V. So let's see what that gives us. This gives us inner product of V and W squared over length of v squared minus inner product of v and w squared. This guy, as we know, is just the length of v squared, and this one is length of v to the power of 4. Now, as you see, these two are the same. This quantity and this quantity are the same, so that's 0. Okay, so we showed that these two vectors are orthogonal to each other. Now I can apply the Pythagorean theorem. So by the Pythagorean theorem, length of w squared is equal to length of inner product of v and w divided by length of v squared times v squared plus length of w minus that. These were the two vectors that were orthogonal, v squared. Now, the second quantity is of course greater than or equal to 0. So therefore, this is greater than or equal to length of inner product of v and w over length of v squared times v squared. Now, this is a scalar again. This is a scalar. This quantity here, this is a scalar. So if you write this down as inner product of this vector with itself, you will get inner product of v and w, inner product of v and w divided by norm of v squared, v, and itself. Okay, so what is that? If you take the scalars out, we get vw squared over length of v to the power of 4 times vv. And notice that the inner product of v and itself is just length squared. So this is going to be inner product of v and w squared divided by the denominator is length to the power of 4. This is length squared, so that's length squared. Okay, so let's see what we got. What we got is length of w squared is greater than or equal to inner product of v and w squared divided by length of v squared. Now, multiply both sides by length of v squared, and then take the square root. So we'll get length of v, length of w is greater than or equal to absolute value of inner product of v and w. So this completes the proof only for the case when v is not 0. If v is 0, then, this is not the complete proof. If v is 0, you'll have to check that separately. But that's actually a very straightforward case. It's one of the exercises, but it's actually the easier case. Because when v is 0, if we go back, inner product becomes 0. That's something it can be proved pretty easily. Length is also 0, so both sides are in fact 0. And again, both of those two things must be proved, that inner product is 0 and length is 0, and therefore both sides are 0, and you have in fact the equality. Okay, so that's nice. Now that we have this inequality, we know this quantity of inner product of v and w divided by norm of v, or length of v times length of w, is always between -1 and 1. Since this quantity is between -1 and 1, we can take its cosine inverse, and that would give us the angle between two vectors. So the angle between two non-zero vectors v and w in Rn relative to a given inner product is defined by cosine inverse of inner product of v and w divided by length of v times length of w. Okay, so now we will do an example on this. Find the angle between these two vectors relative to the standard inner product and once relative to this inner product. So we will do the standard one first. So the angle is cosine inverse of inner product, so 1, 2, -1, dotted with 1, 2, 1, 1, 3 divided by length of each one of them relative to this inner product. So it would be square root of 1, 2, negative 1 dotted with itself, and also square root of 1, 1, 3 dotted with itself. Okay, so if you look at that, the first one becomes, this is again cosine inverse, the numerator becomes, so if you write it down, we get 1 plus 2 minus 3 divided by something. It actually doesn't matter because it is just pi over 2. The cosine inverse of 0 is pi over 2. So this is relative to this one, to the dot product. Relative to the second inner product, we'll have to first find the inner product. So inner product of 1, 1 to negative 1 and 1, 1, 3. So what we do is this. We do 1 times 1 times 1 plus 2 times 2 times 1 plus 3 times negative 1 times 3, which is 1 plus 4 minus 9, that's negative 5. So that's the inner product of these two relative to this given inner product, because if you go back, inner product is 1 times x1, x2, 1 times 2 times y1, y2, 3 times z1, z2, and then you'll have to add those three numbers. So that's what we did. 1 times 1 times 1, 2 times 2 times 1, 3 times negative 1 times 3. So that would be 1 plus 4 times 4 minus 9, that's negative 5. Then we will do the norm of each one of them, or length of each one of them. So you do 1 to negative 1 inner product with itself. That will be 1 times 1 times 1 plus 2 times 2 times 2 plus 3 times negative 1 times negative 1, which is 1 plus 8 plus 3, that is 12. Then we will do the inner product of the other one with itself, which is 1, 1, 3 with itself. 1 times 1 times 1 plus 2 times 1 times 1 plus 3 times 3 times 3. That is 1 plus 2 plus 27, which is 30. Okay, so the angle is cosine inverse of inner product. So if we go back and look at the inner product, that's negative 5 divided by root 12 times root 30. So this is the angle between these two vectors. Okay, so that's the final answer. You have the angle is obviously different relative to different inner products. Okay, so finally, the last theorem that we're going to prove today is about the relation between orthogonal vectors and linear independence. Suppose v1 through vk in Rn are orthogonal non-zero vectors. So this is for emphasis. Anytime I talk about orthogonal, I assume that they are non-zero, although I emphasize that here. With respect to some inner product, then they are linearly independent. So let's assume that they are some linear combination is 0. Then we will show that the coefficients must be 0. So suppose C1 through CK are scalars such that C1V1 plus CKVK is in fact 0. So we will show that all these coefficients are 0. So how do we do that? We will just find the dot product of this one, inner product of this one, with one of the vectors, and then we use the fact that they are orthogonal. So let's do inner product of C1V1 plus CKVK with V1. This would give you C1 inner product of V1 and V1 plus C2 inner product of V2 and V1. Now, we know they are orthogonal, CK inner product of VK and V1. We know they are orthogonal What that means is that all of these inner products are all 0. So this is 0, this is 0, they're all 0. Which means this is equal to C1 inner product with V1 and V1. On the other hand, this sum is just a 0 vector. So if you look at the inner product of 0 and V1, that is relatively easy to say that that's 0. Why? Because that's just 0, 0 inner product with V1, which is 0 by linearity times the inner product, which is 0. So that means C1 times inner product of V1 and V1 is just 0. But V1 is non-zero. By assumption, V1 isn't 0. So now by positivity, inner product of V1 at itself is positive. So what does that mean? It means C1 must be 0. So now we got that C1 must be 0. Now that means C2V2 all the way to CK minus CKVK is 0. And once you have 0 for this one, then you can either repeat the argument, or better yet, you can use induction. So we can prove this. I will let you do this one, but that's the main idea. We can prove this by induction on K. So basically you go ahead and at the beginning you add that we're going to use induction, prove that for K equals 1, which is pretty clear, and then assume it is true for K minus 1, prove it for K by doing the stuff that we just did to show that C1 is 0. We know these are linearly independent, therefore C2 through CK must also be 0, and then we are done. So if you have a bunch of vectors that are orthogonal to each other relative to some inner product, then they would have to be linearly independent. So we will continue with this one next time. Next time we'll talk about how to find bases of orthogonal vectors. I will see you in the next video.